Dr. M.K. Ilamponan, sir.
Yes, madam.
Sir, shall we start another 2 minutes, sir?
Yes.
Okay, thank you, sir. Okay, ma'am. Good evening, everyone. Myself, Dr. V. Jayalakshmi, Professor, Department of EEE, Bharat Institute of Higher Education and Research. So, I welcome you all for the 4th day, 7th session of AICTE Training and Learning Academy sponsored 6 days online faculty development program on recent trends and advancement in integrated power systems. It's an honor and privilege to introduce our distinguished resource person, Dr. M.K. Ilampurnan, who is not only a distinguished resource person, but also the driving force for organizing this faculty development program successfully. His visionary thinking, meticulous planning, and unwavering commitment have seamlessly brought together a distinguished panel of esteemed speakers, transforming ideas into a well-structured and impactful program. Sir, currently serving as Professor in Department of EEE and Dean IQAC, Bharat Institute of Higher Education and Research. He possesses deep expertise in electrical engineering. Sir has obtained his bachelor's from Government College of Engineering, Bargur, and he has obtained his master's from Anna University in the High Voltage Engineering. He pursued his PhD from IIT Madras in the year 2011. He is having around 24 years of experience out of 19 years in teaching and administration and 5 years in research development. He has published more than 25 papers in various reputed journals and conferences. Sir has obtained patent for online assessment of moisture in power transformer, universal power bridge, air pollution monitoring system in Metropolitan Hospital using wireless sensor network, and improved voltage compensation technique for long sag condition using AC chopper, differential protection for single phase transformer using Arduino with IoT. Has received NPTEL Discipline Star in electrical and management domains. He also got NPTEL Topper Certificate for various NPTEL courses. In his academic journey, he has been working in many responsible positions. He has coordinated and supported various accreditation systems like NAC, NBA, IET, and ABET. Sir is responsible for creative design for prominent model of moisture estimation for partial discharge with condition monitoring, power and instrument transformers. He worked as research assistant directly with the testing and calibration division and instrumentation engineering. He has tested various power transformer at site ranging from 100 MVA and calibrated various instrument transformers from 11 kV. He is chaired hiring committee for new core faculty members of School of Electrical and Chair for API Promotion Committee. Beyond his professional and technical accomplishment, he is the pillar of support, inspiring all of us with their passion for learning and commitment to excellence. I welcome you once again. Now, I hand over the session to our resource person.
சரி போய் படுத்து தூங்கிட்டு வருவேன் ஒரு 2 மணி நேரம் கழிச்சு வரையா நேத்து மாதிரி
Dear participants, kindly mute.
என்னதுடா தமிழ்லடா நாளைக்கு
Dear participants, please kindly mute.
தமிழ் நாளைக்கு எழுத போலையா சரி அப்படியா
Madam, my PPT is visible?
Yes, sir, it's visible. It's not in screen share mode, sir. Slide share.
Slide show mode.
Yes, yes.
Okay, I think I have to share it completely. Now it is showing, madam.
It's not showing, sir. Okay, sir. It's showing.
Good afternoon. I am Dr. Ilam Purna, and thanks for the introduction, Dr. Jayalakshmi ma'am, and for organizing such a wonderful FDP and sponsored by ATAL. Thanks to all the ATAL members who have sanctioned this FDP. We'll directly move on to the content. My voice is audible, madam?
Yes, sir, it's audible. Clear one.
Okay. So we are going to discuss for the next 1 hour at least regarding the condition monitoring and diagnostics of the power transformer. So a brief overview of two kinds of methods. One is offline condition monitoring method, and another one is online. In the offline condition monitoring method, we are going to discuss about the degree of polymerization, furan analysis, interfacial tension analysis, and acidity of oil, then dielectric breakdown of oil, insulation resistance test. Along with that, we will have polarization index, then dissipation factor, dielectric response methods, which includes recovery or return voltage measurement, RVM, famously known as RVM, and PDC, the polarization depolarization currents, then FDS, frequency domain spectroscopy, and we have the frequency response analysis, which is famously known as SFRA, including the sweep frequency response analysis, and transformer turns ratio test. So these are the offline condition monitoring methods we are going to discuss. Depending upon the time, we can go in depth, or we can have overall understanding. Then online condition monitoring methods will have dissolved gas analysis. In that, these are the 3 stages which we will discuss when it arises. Then photoacoustic spectroscopy, then online hydrogen gas detection. Then there are various interpretation methods for this dissolved gas analysis, and partial discharge detection. So these are the things we are going to discuss. Apart from that, there are some recent trends which we'll add at the end of the slides. So this is one of the interesting study which I want you to bring it to the forum and understand. And what is the actual failure statistics in the transformer? As it is, you can see here, 50% of the failure arises because of the winding deformation or winding problems. Then insulation problem is 8%. There are other problems like loosening of nets, bolts, structural changes, everything. If put together, it is 20%. Then because of bushing, the transformer may fail. That is around 7%. Then onload tap changes, OLTC. That is one of the major cause for the transformer failure. So from all these things, you can get an idea which part of the transformer will cause a major failure. Before entering into the transformer as it is, I would like to have one input from your side. What is the necessity? There are many equipments in the transmission line which are connected. Electrical equipments are connected in the transmission line uh, right from the generation, transmission, and on the other side, that is the distribution. But most of the people focus, that is industry focus only on transformers. Is there any specific answers from your side? Why people focus more on transformers? Any answers?
It's one of the costliest equipment, sir.
Yes, yes,
Say-
yes, obviously. So it's one of the, or not the only costliest equipment. The next costliest equipment will be like your lightning arresters. So this is the most costliest equipment, and the power transfer is one of the important thing, function which it does. First, let us see what are all the common parts in the transformers. The active part, actually where the power is getting transferred from one circuit to another circuit. Is there any idea? It's a very fundamental question. Anyhow, I just need to know from the audience. The transformer actually transfers power, but can it add on to the power? Is there any view about it? Can it increase or decrease the power? A very fundamental question.
So depending upon the type of transformer, sir, either step up or step down, like please.
No. The power is only transferred actually. We have a variation only in voltage or current. The V into I is common on both sides. Okay. So the kVA rating, you can see the kVA rating of the transformer, which is in the nameplate details. It is same to both the sides. Only the voltage or current will change depending upon the types. Okay. Anyhow, there is no power addition in case of transformer. There is only power transformation. That's the very name of the transformer. And the cooling system is another important thing. Why we need cooling system? Anybody? Is it necessary?
Yes, sir. Otherwise, heating effect will damage the transformers. Insulation, it affects the insulations.
It affects the insulation. Okay, to an extent it is okay. So, any idea about the types of the cooling system? Anybody? Most of the people are electrical engineers. So, any idea about types? One or two types. Here I have even mentioned it. Okay. So the normal distribution transformer you have seen, right? What type of cooling system we have in the distribution transformer?
Oil cooling system, sir.
Oil is obviously insulation
Okay.
and also a cooling agent, but how the oil get cooled?
Air forced cooling, sir.
We use forced cooling in the distribution transformer.
Yes, sir.
No, it's a natural conventional flow, or you will use fins. It is there is no pump to pressurize the oil. Only when there is a pump, it is forced. So it's a normal flow of oil through the fins. They call it as natural oil flow, right? Then that is ON. Then ON, FC means you will have fans, sorry, pumps. Then forced oil means you will have pump as well as fan. Forced oil and forced cooling. So there are, you can put the permutation and combination. There are different types of cooling system. But distribution transformer, we have only natural flow of oil. Of course, they may add some fins. You would have seen the fins. Conservator, why we need conservator? Most of the people are electrical background, I suppose. Any idea of conservator? Yes. You would have seen one big tank above the transformer. That is nothing but a conservator tank. It is there in all the transformer except for the sealed transformers. Any idea why it is there?
For storage. Yes, sir.
No, it's not storage actually. See, when we manufacture the transformer, you can't fill the oil till the top of the tank. Okay, so when the actual power transfers, you will have loss of power. It is, you know, what are the losses of the transformers, right? Any idea what are the losses of the transformers?
Iron loss, copper loss.
Iron loss, copper loss, general. Next, any other thing? Okay, apart from this, you will have dielectric loss also. So iron loss and copper loss, of course, it is one of the important loss. Iron loss is also called as core loss, and the core loss and iron loss, the copper loss will contribute for the heat exchange between the transformer and the oil. What will happen when the oil gets heated up?
It start
Evaporate.
expanding, sir.
Yes, yes, it will start expanding.
It
So
gets
if
vaporized.
Evaporated, sir.
it will not get vaporized. We use a different kind of oil, mineral oil, which is not so easily. If it is vaporized, means it will catch fire. Okay. So the thing is, actually you will have expansion of the oil, and if you are tightly packing the transformer, what will happen? If the oil
The
expands,
expansion can't take place.
expansion can't take place, or otherwise the tank will burst. So they will provide a tank, so where the oil can expand and contract. So the space is not provided in the tank, whereas that is in the transformer tank, whereas you will have a separate conservator tank where the space of oil expansion is provided. Can you understand and relate? Expansion will happen in the conservator tank, whereas the transformer main tank will be full of oil. Clear?
Yes, sir.
Okay. So if the oil expands, then there will be some air in it, right? In the conservator tank, there will be air. Where that will go?
It will go through the vent gap.
Wind gap.
Vent gap.
Vent gap.
To the
okay.
breather.
To the breather. Is there anything in the breather?
Yes.
Yes.
We call it as silica gel breather.
Yeah, silica gel breather. Why we are keeping the silica gel there?
So to absorb the moisture content.
Why we need to absorb the moisture?
So when the oil expands, no, it will go out, and when it cools down, no, it condenses, it will absorb the moisture from air.
Oh, good. Very good.
So will,
what happens when the moisture enters the oil?
The dielectric strength of the oil will be reduced.
Only dielectric strength of the oil?
I think so.
Not only a dielectric strength of the oil acts as a carrier, and it will go and impinge upon or impregnate with the paper. So paper or dielectric strength also will reduce. So we need to prevent We need to prevent this inflow of moisture. So we keep a silica gel. Of course, the silica gel will be initially starting with a blue color, then slowly transformed into pink color, then become completely, if it absorbed moisture completely saturated, it will become white. So again, you have to heat it up and make that functional. Okay. So anyhow, this is closely related with what we are going to deal. So one of the major cause of concern is the amount of moisture which is absorbed from the atmosphere. So they are trying a lot of methods to avoid it, but it is not possible. It's like closing our nose. You have to breathe, of course. If there is a pollution in the air, what you have to do? You have to put a mask, or sometimes you have to put an oxygen cylinder. That's the only escape. But you can't stop breathing, right? So similarly, for you can consider the entire transformer as a human being. The lungs are the conservator tank, and it breathes to the through the conservator tank. You can't avoid the breathing. Next, we'll come to the next part, which is very important part: bushing. What is the need for keeping the bushing? In most of the laboratory transformer, we don't have bushing. So most of the people are the teachers, I know. So bushing is a new concept, maybe when you deal with power
For
transformers.
connecting the conductors, sir.
Connecting the conductor, you can put a simple wire, right? Why you need bushing?
For connecting it to high voltage lines.
High voltage lines, maybe a bit clear. What do you mean by high voltage lines in the sense?
So the bus bars.
Anything, whatever may be the thing, high voltage line or bus bar. It may be on either side, right? It may be in the substation or it may be in the generating station. So power transformer are used on both sides. So what is the necessity of bushing, I'm asking? It's you are telling about the end connection of the bushing. I'm asking why bushing is there in between the line and the transformer.
I think
For
it provides
supporting
insulation also.
purpose.
No,
Insulation
no.
between the internal and external connections.
Yeah, perfectly. It is for the
Am I
insulation
correct?
between the winding and the tank. If you bring a simple wire, it will just short circuit and the tank will get energized. Or you will not serve the purpose. So you need bushing for the exit of high voltage from the winding directly to the line and bypassing the tank. The tank should be insulated from the actual conductor. So that is why the bushing is there. Of course, we can go in on and on, but we are focusing only on the transformer. I am not focusing on cooling system, conservator tank or bushing, but I need to cover it. And I need to focus on the internal transformer before going to integrate the OLTC, the on-load tap changes. What do you mean by it? Any idea?
That
Why
is
we need?
changing the number of turns in the transformer windings when it is on load.
Okay, good. Why we need it?
For to avoid the, that is to maintain the voltage regulation. That is output voltage
Continuity of
constant.
supply. Maintain the continuity. No need to.
In order to provide the constant voltage at the output which we require.
We need to match the grid voltage.
Yeah.
We need to match the grid voltage, and very good. Suppose if one of the transformer is operating on a different voltage level, what will happen?
So I think it can't be parallelly operated. The main condition is the transformer voltage should be same. No, an internal current will flow in the between the
That's okay.
transformer.
If it is there, what will happen?
I think
You
the
are right,
output
perfectly
will,
right.
yeah, the losses will increase.
Losses will increase, and there will be circulating current between the transformer.
Yeah, circulating current which leads to losses.
So that is the main condition. I am not going to deal about any of this part. I am going to deal only with the active part of the transformer. So my focus is only on the active part.
Okay, sir.
Am I clear? Okay. Next we shall proceed. So this we have already dealt in detail. We'll go move. First, what are the two insulations which we are going to deal in the transformer is one is insulation paper, another one is oil. This is like a beautiful combination, which is actually sustained for almost 150 years. So why this combination is taking place? Why we have a paper oil system? There are many people are tried many things like varnish. There are many things. You can't even imagine mica based some insulation sealed transformers. In fact, solid transformers. People have tried a lot to change this combination, but still, even after 150 years, the solid standing is there between the oil and the paper. What is the actual beauty of this combination? Any idea? You can even see in the laboratory, we don't have, we have simply mica insulation. That is different. But a power transformer needs oil and paper. There is nothing equivalent to it. Why this particular combination working well? And in fact, most of the transformer which has been established is working almost like 100 years or something. The age of the transformer is also very high. Any specific reason for this combination? Okay. Say the thing is actually paper is a porous material. You can see even the normal paper. Can you dip it in oil and see what will happen to the paper?
Paper absorbs.
Paper absorbs the oil. Okay.
Oil.
What will happen? Can the paper be without any pores? Can it be manufactured without a pores? Pores means some micro openings. Paper is obviously with micro pores, right? If it is there, if there is oil, what will happen is that the oil will go and fill up this particular pores. Okay. So any insulation, you can take any insulation, metal, anything blessed thing manufactured in the world will have some defect, including human beings. So you have the particular void which is there in even in the most perfectly manufactured metal or insulation or anything. But when you combine the solid and liquid, what will happen is it will go into that particular pore. The combination of these two will increase the dielectric strength to an enormous value. So that is the beauty of this combination, and it is actually lasting for 150 years. People have tried a lot. There is no replacement for this. Okay, we will move on to the next thing. When we take paper as it is separately, this insulation paper, there is one thing called as degree of polymerization. What do you mean by degree of polymerization? Any idea? What is polymerization? General idea of polymerization? Polymers, no idea. Okay. So there is one single glucose or a compound when it is structurally connected
It's
by van
repeated
der Waals.
chain.
Repeated chain, not only linear chain, it will have multiple cross links. Okay.
Okay.
So that is the strength of this. So paper is one kind of such a polymer. It's a cellulose polymer. Okay. So the degree of polymerization means how many number of compounds is there in that particular pair. You can see here I have given 1000 to 1400. That is a typical DP value. DP value means degree of polymerization value. You have seen our normal notebooks, right? after 10 years, have you taken that notebooks and seen what happened to the notebooks? Have you seen that? Most of the people would have experience in the life, right?
Yeah,
10
yeah.
years notebook, what happens to that?
The paper will break, like if you test a paper, it will break down.
It becomes brittle.
It's
It's
exact
a
brittle.
brittle, and the color change will happen in between.
Yeah,
If you
color
take 5
change
years
mainly
means
it
color
happens.
change, then brittle. So these are all the things. Actually, the notebook is a perfect thing to understand our transformer paper. What will happen is first initially the moisture will absorb, the degree of polymerization is reducing. Then finally, if the degree of polymerization drops to 100 or 250, what will happen is it will become brittle. That means it will just made into dust. So it will just mix with the oil. It will become another dust in the oil. So that is the worst kind of the thing that will never happen. In fact, it will not happen in 100 years. So it may be happening in maybe another 100 years, 200 years. We don't know, right? So if you want to test the insulation of the paper, what you have to do is you have to take the sample of the paper. So how do you take the sample of the paper? You have to again open the transformer, take the paper. That is not practically feasible. Okay, so this is even though it is looking very good and a promising technique of understanding the insulation strength, this is not practically viable option. So I'm just telling this is one of the option, but it is not practically feasible. So what we will do is when the DP reduces, what will happen is it will release certain uh, compounds in the oil. So it's exactly like our blood. So when a person has any problem in the entire physical body, what will happen is first thing to take that to all the parts of the body is blood. So imagine a person is having a kind of abnormal tumor or something. So it is very deep inside the body. But when it bursts, what will happen is it will just emits its pus into the oil. That is our what do you call it as blood. So what the doctor will do is first you do the blood test and come. So similarly, transformer, we will have the oil test. So it's comparable to our human body. So when we take the blood test for the human, it is similar. We take oil test for the transformer. So in the oil, there is a reflection of furans. Furans are the one of the important compound. But what happens is you have to take the oil, you have to put it in a HPLC, that is high performance liquid chromatography, and you have to pass that oil, and it will separate the different content of the furans which is available. It will show the ppm level, parts per million level. So that and all is the next thing. So it is not possible for me to open the transformer and take the paper as it is, but I can always get in touch with the oil, which is an indirect indication of what is happening in the paper. So I take the paper oil and see what is there in the paper. Now this is the typical compounds which are released when there is a decrease in the degree of polymerization. Out of these things, what is very severe is the 2-foraldehyde, 2-FAL. Okay, so that is very direct indicative of what is the degree of polymerization in the. So there is a direct correlation between 2-FAL and the actual DP value of the paper. So can you relate it? I am not directly touching the paper. I am taking only the oil, and in the oil I am testing what is the level of ppm of 2-foraldehyde. So if the 2-foraldehyde is in the range of 0 to 0.1, it means that DP value is good, healthy. It's above 700. If it falls to or increases to 1 ppm, then the DP value will fall. It's a indirect correlation. So when there is a rise in the FAL, that means there is a decrease in the DP value. That means more amount of compound is getting polymerized, depolymerized. Okay, we'll move on to the next one. as I said, it's like taking the blood test. So we take the transformer oil and test the interfacial tension. What is the interfacial tension? Is like you would have seen in the beakers of oil, right? Have you seen the beakers of oil? Glass, you have to take glass beakers and see the sides of the beakers. Is there any difference in the surface level? Have you ever observed that? When you pour the oil in the beaker, it has to be stable, and you have to see the sides of the oil inside the beaker. Is there any difference in the surface level? Have you observed it? That is in the boundary between the glass and the oil. Okay. So that will be differently the surface change, that is due to the interfacial tension. That is a way to measure the American standards, the ASTM, way to measure the interfacial tension. You have to put a circular ring inside the oil, and the amount of the force required to move it. That is measured in dynes. Actually, dynes is nothing but 10 power minus 5, dynes per centimeter is 10 power minus 5 Newton. So it's very lesser. So we are given in dynes. So it depends upon that. The IFT is changing. If the IFT reduces, that means it is degraded. Okay. So that is the idea here. Of course, I have given acidity, and acidity is another way of understanding. There will be more acids which will be released. So you need to neutralize with the KOH, that is potassium hydroxide, and see how much amount of acidity is present in the oil. Higher the acidity, that means more depolymerization has taken place. And another way is this is very standard way of doing it. You take the oil out of the transformer and you measure the breakdown strength of the oil. You apply. There are some standard test equipment. You can take the electrode, which is actually mentioned in almost all the standards. What would be the size of the electrode? What should be the distance between the electrode? And you have to apply the voltage and see what is the breakdown voltage of the oil. So it has to break between this electrode. So actually we have IEC standard here mentioned, but there are adequately different standards also. Even our Indian standards are there, but almost it's all derivative of these standards. So we have to observe what is the breakdown voltage. If the breakdown voltage falls, that means we have to take action. It's like changing the blood. Okay, so we have to pump out all the oil, pump in again the oil, a new oil, and it's like putting it fresh. You would have seen many of the cine stars would have done the complete change in the blood to maintain their age. Okay, so there are means of doing it. Similarly, transformer can be maintained with age if we pump out the oil and pump in the fresh oil. Okay. So next, the insulation resistance test. First of all, any idea about the insulation resistance? What do you mean by insulation resistance? Any idea of insulation resistance?
It is
It
the
does not,
dielectric
it does
strength
not
of the
allow
insulating
to
material.
does not allow to conduct electricity.
Insulation resistance.
Sir, to oppose the flow of leakage current?
It is
Not
the
opposed to
resistance
flow.
of insulating
Actually, it is
material.
causing the leakage current.
Okay.
Actually, when you take a dielectric, initially you can assume it as a perfect dielectric. That means it is a perfect capacitor. As the age increases, what will happen is you will have the deterioration in the capacitance value. So that is one way of understanding it. Or if you model it, what will happen is you will have a parallel resistance. So there will be a capacitance as well as there will be a parallel resistance. Some people used to put it in series also. It's all the convention. We will have it as a parallel. So what will happen is there will be two types of current flow. I hope most of us are electrical engineers who would have studied field theory. So there are two types of current flow. What are the two types of current flow? Any idea? If you study Maxwell's equation, you will
So
understand.
AC or DC?
AC. Okay. That's too fundamental. I'm asking two types of current flow from the technical perspective. This is just what a signal perspective. AC means you will have sinusoidal or some square or something, but I'm not speaking
Generation
about.
to load, load to generation.
Sir, conventional current and the current due to flow of electrons, and another is conventional current.
No, conventional current is flow of electron. Another is what is that? Another.
Generation side to load side to generation.
No, don't think too much complicated. If you have gone through the Maxwell's equation, you can answer this question. One is called as conductive current, which where the electrons flow from one side to the other side. Another one is called as the displacement current, which happens in the capacitance. So as a dielectric, there should be only displacement current. There should not be any conductive currents ideally, but it is not possible. So if the conduction current is increasing in a dielectric, that means there is a problem. Or in other words, how do you relate the current and resistance? What is the relation between current and resistance?
Ohm's law.
V is
Tell
equal
me,
to I
what is
into R.
the
I into
V equal to I
inversely
into R.
proportional, sir.
yes,
It's inversely proportional.
yes, obviously. So conduction current increases means what will happen to the resistance?
It decreases.
Decreases.
It
So
decreases.
decreases. So when you have a perfect, what do you call it as a good insulation resistance level, it will be measured in mega ohms, and the instrument to measure it is called as megger. If the insulation resistance drops, what it happens? That means conduction current is increasing. That means your insulation strength is
Fails.
decreasing. Okay. So that's the idea here. So when you do, these are all simple tests. A company does not complicate the issue. They can't buy all the complicated things. Only that is possible only for academic institution doing research. Company will not do this kind of research and all. They do very simple test and understand whether insulation will withstand or not. See, when you go to any sophisticated hospital, what they will do now? They have purchased a lot of testing equipments. They will send you nook and corner to use that instrument. But when you go to a simple man who is having only single clinic, having only stethoscope, he will tell you what it is. What's the problem? Of course, he should tell. What he will do, he will just put a stethoscope and tell, okay, this is a problem you are having. Maybe you want to, you can do this test for your confirmation as well as my confirmation. Similarly, insulation resistance is a typical doctor way of testing the transformer. So if the insulation resistance is high, that means the insulation is good. If it is less, then it is bad. Simple test, yes or no, right? But the problem is insulation resistance also varies depending upon the charging or discharging current. So this is another new term I'm introducing. So what they have done in standards is they will actually put a voltage for 10 minutes and hope so after 10 minutes there is no charging current flow. That means your insulation resistance value has to stabilize. So the transient flow is overcome. Many people would have done electric circuits, right? So there is a transient current. So the transient current will be overcome. So they will measure at the two conditions. One is 1 minute insulation resistance, another is 10-minute insulation resistance. Afterwards, the convention came. There is a thing called as polarization index. So they found out the ratio between the 10 minutes insulation resistance and 1 minute. Nearer this value, that means 1 minute resistance and 10-minute resistance are same, means that means there is no charging current flow, or lesser time it is getting charged. That means your insulation is gone. So higher the thing, it will be better. Okay, so that's the idea. Very simple idea, but it is actually giving a lot of information about what is happening inside the transformer. And then the dissipation factor method. To understand this, I need to again go into this. Already we have discussed that the dielectric can be modeled with one resistance in parallel with one capacitance. So when you apply an alternating current, it gets, as we discussed, two types of current are there. One is conducting current, another one is displacement current. IC is capacitive or displacement current. IR is the insulation resistance current. Now only we have discussed what happens when the capacitance current and to the resistance current when it ages. What will happen? As the aging happens, what will happen to the resistance?
Decreases, sir.
Obviously. So what will happen to the current then?
Increases.
Increases. That means your component, you can see the right hand side, I hope my arrow is visible to you. Pointer is
Yes, sir.
visible.
It's
Okay.
visible, sir.
Okay. So here you can see here, if it is completely capacitive, then you have the voltage and the capacitive current is out of phase. That means a 90-degree off. When there is both the resistive current and capacitive current, what will happen is you have some smaller resistive component here. That means your current is not completely capacitive, but it is a phasor sum of IC and IR. So you will have a small angle between ideal capacitive IC and capacitive current IC and your real current I. So there is an angle phasor between I and IC. This is called as what angle? It is del, or the displacement angle. And the factor, what is the factor is IR by IC. How much resistive current is there to the capacitive current? That is called as dissipation factor. This is one way of measuring. There are many instrument which is available, and most of the industries, they have what you call it as a tan delta measuring equipment. But it is not so complicated. You can even use a sharing bridge. So in laboratory cases, we have sharing bridge for measurement of capacitance. That much is sufficient to understand this idea. And the other way of doing it is a capacitive current. That is, you can completely avoid capacitive current. You find the ratio between IR and I, then it becomes power factor. So in this case also, where the IR increases means the power factor will also, there is a relation, right? So what will happen to that theta? It is decreasing. So cos theta is increasing. So this is the problem. So we will have a power factor as well as dissipation factor. Both can be used as an indicative of what is the actual thing happening in the insulation. So it's one of the fundamental tests. Like we decided only based upon the insulation resistance. Now we have both insulation resistance and the capacitive current. So this is more powerful compared to the previous one, what we did with the insulation resistance. So this will give more idea of what is happening in the capacitance or dielectric value. Okay. Now let us move on to the actual core of our testing of insulation materials. That is what is happening. We should now think the insulation material as a capacitance. So the capacitance, what is the actual function of the capacitance? Any idea? Or how it behaves actually? when you apply a DC voltage with the capacitance, how it will behave. Don't think about AC voltage, alternating current voltage. You just think about a direct current. When it flows to the capacitance, what will happen? Most of us are electrical teachers, I hope so, and you know how the capacitor will behave when you connect to the voltage source.
Charging, sir.
Charging. So how long it will charge?
Till the voltage across capacitor should be equal to the supply voltage.
Exactly, beautiful. So the thing is, actually you have different voltage levels between these things, and that means you will have a current flow as long as you have the input voltage not equal to the capacitance voltage, isn't it? So what, that is same thing idea is used here. So I connect the switch S1. What will happen? The DC voltage is connected to the insulation. Of course, you should maintain S2 and S3 open. So only the current flows from the voltage source here. You can see my pointer. The current flows from the voltage source here. It flows through the S1 to the insulation. This is, you should think as a capacitance. It is getting charged. Okay, so as you said, if the voltage becomes equal, what will happen? There will be no longer the current flow. Am I right? Is it,
Yes,
do you understand?
yes,
Yeah.
sir.
Okay. In that condition, what will happen? Maybe what do you call it as infinite time? Okay. Infinite time means I can't mention exactly, but there can be standard something beyond this time. Usually they call it as tau. Okay. So you can open this S1 and close this S2. Then what will happen? You have to think, assume this as a capacitance, and now I am closing the S2 and opening the S1. What will happen?
It may discharge.
It has to discharge. Okay. I'm not allowing it to discharge completely. So after a certain time, what will have? What I am doing is I am opening this S2 and closing this S3. What will happen? I'm not allowing it to discharge completely. That's very, very important thing to realize. If it is completely sending its current or discharging, then what will happen? There will be no energy in the capacitance, but still some energy is there. So I am suddenly opening this S2 and closing the S3. What will happen?
Capacitor gave the charge to voltmeter.
Voltmeter cannot consume, na? It is not a load. It has to measure. If it is consuming, then it is not. Then voltmeter loading will happen. That's not the idea here. The charge is not flowing, right? So what will happen? It appears as a voltage. Very simple logic, right? So initially charge is flowing from the battery, here the voltage source, to the capacitance. So this is getting charged. That means it develops voltage across it. Okay, after a particular point, this voltage development will stop because the charging current flow will stop when they both become equal potential. Suppose if you close it, this one, then open it, what will happen? The charge get discharged through the S2, but I am not allowing fully. So suddenly I am just opening it and here closing it means again it has to develop the potential. That potential can be measured. Okay, so this is very simple, even though it looks very simple. Uh, it's like actually understanding what is the polarization phenomena which is happening inside the dielectric. So it is done for the entire transformer, you should understand, and we can understand what is actually the polarization phenomena which is happening inside the transformer. So it's studying the physics inside the insulation of the transformer. What are the types of polarization? Any idea? Anybody? Generally, you would have studied types of polarization in physics, right? Maybe long back. Okay. As on now, the polarization is 5 types: electronic, ionic, orientational, interfacial, then hopping. The hopping is very recent phenomena, in the sense lot of research is going on, so I'm just avoiding it. Interfacial is very specific to the transformer. It is between the oil and paper interface and board or the spaces. And the orientational polarization is common. That is, you have a specific domain of dielectric which is aligned to the electric field applied. So all these idea you can get from this RVM measurement. Of course, electronic and ionic, there is no instrument in the world to measure that. Still physics people are trying to measure it. Only God can save them. It is not possible to measure as on now. Right. So I'm just giving the actual picture, what is happening when you apply the voltage. So what I'm doing it, you have to relate it with the previous circuit. So you can see I am applying the DC voltage till a particular time, that is TC. That means I am allowing the capacitance to charge. Then I am shorting it. That means I am allowing it to discharge, not completely. Then suddenly I am opening the short circuit and connecting with the voltage. What will happen is it will develop the voltage, but not suddenly, because the charge has to align itself to form the capacitance voltage. So it will take some time to make it stabilized. In that time, I need to measure this particular slope. That means the rate of rise of the voltage, that is dUr by dt, as well as how much maximum it will reach. All these things will give you approximately what is happening in the polarization, that is especially two polarization, that is the orientation polarization and interfacial polarization. This particular time taken for these to rise indicates how much time the internal orientation is taking to align with the given field. And the maximum indicates how much domain is cooperating to make. So these are all pure physics phenomena which has to be understood. If it is understood, better. But as an electrical engineer, to test the insulation, these two, just an idea, the rate of rise as well as the peak of this return voltage. That much is sufficient to understand whether the insulation is working perfectly good or not. So we need to take it at various levels of age. So this is also a kind of aging measurement. I'm just reiterating the point. So what we are measuring in the recovery voltage method is the maximum voltage which it can reach and the time taken to reach, that is central time constant, and also the slope, that means rate of rise to the recovery voltage maximum. So these three things component are noted. These are all signatures which are used to quantify the dielectric strength. Next, we can move to the next type of measurement. This is called as polarization deployment. This is nothing but the same repetition of what we have done previously. Instead of measuring the voltage, we measure the current. That's it. So we charge again the capacitance. We apply the voltage. We allow the S1 to close. If the S1 is getting close, what will happen? It will goes into the capacitance. The capacitance get charged. If I measure the current during that time, it is called as the charging current or polarization current. And of course, why the current this is getting charged is nothing but because of polarization. Again, when I open this and close this, what will happen? This will depolarize. When I measure the current, it will be like it's a depolarization current. Of course, the current direction will get reversed. So in this, the current direction will be up top to bottom, whereas in depolarization, the current direction will be from the bottom to top. So the direction will be reversed. So obviously, you will have, you can see here, when I apply the voltage, there is a polarization current which is flowing, which is measured by the ammeter. And when it is actually we are opening the contact between the source, voltage source, and moving to the short circuit, then what happens is depolarization with current which is flowing. Okay, how to interpret this? The interpretation is conductivity. So polarization is taking higher value. That means what will happen? Conductivity is more. So polarization, the magnitude, conductivity of current is nothing but what is the relation between the current, conductivity, and the resistance? Any idea?
Inversely proportional, sir.
Resistance is inversely proportional to
Conductivity.
conductivity. Current,
Current is directly proportional.
current is directly proportional to the conductivity. The higher the conductivity means more the current, and so that means you can see here the good the conductivity increases. What will happen? The current will be flowing more. That means you are quickly charging and discharging. That means your insulation is bad. Okay. So that's the idea behind it. Then we go for the same thing. Now it is frequency domain spectroscopy. This is very beauty of it, because orientational polarization mostly respond to the frequency, the amount of the frequency which is thing. So it's like you are you would have seen the spectrum of light, right? What is the colors we observe in the visible spectrum? What are the colors we see in the visible spectrum? BIHER, violet, indigo, blue, green, red. Okay. Okay. So orange and red. So what is the other side? Ultraviolet and infrared, right? So this is the beauty of the light spectrum. Similarly, we have here spectrum of the uh, actual current. So we can see here clearly the beauty of the response. So I'll put the next slide, which will give you an idea. So this is my core research area. So you can see here the lower the frequency, that is from 0.1 millihertz to almost like 1 millihertz. I can directly understand what is happening inside the paper without even touching the paper. I am just giving a signal. It goes and finds what is happening inside the paper. I am not even touching or altering any of the parameter in the transformers. This is the beauty of it. So one of my patent is actually involved with it. So I made a typical model of the transformer, put it in some place. You can relate to the patent. And if I make the oil of the transformer to flow in the model, and if I make measurement in the model, then that means it is reflecting on the actual transformer issues. So it's an indirect way of relating it to it. Absolutely, what do you call it, as phenomenal linkage will be available, in the sense you can understand whether your transformer will work for another 10 years or not. It's a just straightforward answers. So I can understand what is happening in the paper at the low frequency. The only challenge here is I need to have the signal which is having this content. That means I need to have the signal which is having 0.1 millihertz to 1 millihertz range content in a adequate level. That is a very big challenge. Actually, I'm telling here I have shown what you call it as AC source, but it is not a must. Actually, I can even apply impulse, because what is impulse according to your if you have studied the signal processing, impulse contains all the frequencies, but not in same magnitude. So even impulse is sufficient. But AC nowadays there are many people who are making a lot of crores of money out of it. So I'm not disturbing it. So it's like a multi-dollar business. So people are doing it with frequency with adequate voltage level, and they are actually claiming it. So there are two challenges. One is the source challenge, another one is measurement challenge. You have to get a source which is actually providing this much amount of low frequency, and you should have a ammeter which will measure this much amount of lower current. It will be in the order of microamps actually. Here I have shown in the dissipation factor, but it is only, I have already shown that what is the dissipation factor is the ratio of IR by IC. Why I need to measure this ratio? I can directly measure IR. That will give more idea of this thing. That is my one of the research conclusion. So I can measure directly IR and I can relate to the actual problem happening in the transformer. So that is my actual research work, PhD work. And this if I move slightly higher, that is if I move from 1 millihertz to 10 millihertz, what will happen is I can understand how they have designed the transformer. What is actual design parameters in the transformer. If I further move higher, that means from 10 hertz, sorry, 0.1 hertz to 10 hertz, I can understand about what is there in the oil. So it's like scanning a particular person. My beautiful transformer is getting scanned. I apply a very low frequency of signal. I'll get what is happening in the insulation. And if I apply a medium frequency, I'll understand how the structure, inside structure, and is there. And if I apply very high frequency, I will understand what is the actual thing is happening. You can relate to the human being. So I don't know whether the doctors can understand or accept, but the same thing may be possible with some future generation. They may ask, so they may project the electromagnetic radiation at the low frequency. You get an idea of what is inside the body, and in fact you can even understand how the marrow or how the internal cell operation you can understand. Maybe if you give a medium frequency, you can understand how the skeletons are connected with the fleshes and everything. And of course, if you give another higher electromagnetic spectrum, you can understand what is blood. So obviously for me, the transformer is like another human being. So by varying the frequency, I can understand what is happening in the transformer, right? So that's the beauty of these interpretations. I hope this requires a lot of study and understanding. So I'm just giving an overall view and just moving it. Next comes another favorite area, that is frequency response analysis. I have published papers in this in IEEE. Then it's like a signature. So, exactly like our PQRS signal of heart. So I take a transformer, I apply the range of frequencies in the actual winding, and I can take multiple way of the currents and record the response. And of course, this is the frequency response of the transformer. I have taken it across three phases. That means when I connect one phase, the other two phases are connected to the ground along with the ammeter. So it's a kind of response, right? So I'm not going in deep of it. You can verify. There are a lot of papers which is done about. The thing is, there are what is the thing I can understand by applying this FRA, the frequency response analysis. So up to frequency response analysis, what I have discussed there is about the dielectric, and this is also about the dielectric. But what is done here is it even involves the entire core. So if there is any problem in the core, it will be displayed. If there is any problem in the magnetic structure, it will display. It will, if there is any problem in the connection, it will display. So all the things can be taken from this FRA. So this is the connection. Usually people does like this, and you can see here I am injecting the voltage here, and you can take a reference signal. It may be from the end of the bushing, that is earthing connection to the bushing, or it may be from the tank itself directly. Okay, so this is like you apply to one of the winding, the other two windings you can short it and you can connect it to the earth, and you can measure with some measuring devices. Of course, you can calibrate this voltage to current, and that is what you are observing here. There are many ways of doing it: open circuit and the short circuit. There are interwinding test results will be there. Then, of course, the reference data acquisition can be done, and the comparison can be done with three types. One is actually you take the same person, you can measure him the heart pulse at the age of 10 and at the age of 50. You can see the difference. That is one thing. Suppose if there are two people, brother and sister, or brother and brother, or sister and sister, that's all the brotherly relation or sisterly relation, right? So you can put a PQRS between these two, or you can take a similar kind of transformer. It may be you can take like people with 25 years of age with another 25 years of age, compare them, PQRS wave, and you can understand what is happening inside. So these are all like a comparison of FRA. So FRA is one of the best techniques so far, and nowadays they have standardized it a lot, and people are industry is actually they have to give along with the nameplate details, the manufacturing details, FRA details also. Previously they don't give, so that's why we went for the twin sister and the things. So it's like obviously you can use all this juggleries of artificial intelligence and the comparison, and you have correlation. So these are all academic research. You can take much more of it, and you can compare. You can come up with your own theories. So these are all for publications. You can note it down if you want. Good. So now, what does the FRA gives? The FRA will give idea of the radial deformation. That means the buckling. You have winding which is very cylindrical. You see there will be a buckle. That means the winding is pushed out of the shape. That is actually resulting in the shifted frequencies. Axial deformation, that means winding is moving on the top. That also can be seen from the shape movement. You have to relate with the FRA shapes, right? Next, the short circuit, of course, there will be shift in the frequency. So you have to relate to the previous slide. You have to keep this in mind. I should have put it here. So these are all the resonant frequency. You can see the tip points, these tip point, this tip point, this tip point. What I'm speaking is the shifting and the moving. That is moving on the right side or left side. So this is what I'm speaking about. So you have to relate with the reference and the present measurement. So different thing. Radial means it will be shifting. Axial means total shape will be changing, and you will have rightward shift when it is the winding is short circuit. If it is an insulation failure, there will be leftward shift. If there is a bulk movement, there will be total distortion. in the low and mid frequency ranges. So the core fault, of course, this is very beauty of it. If there is any grounding fault, there is any short circuit, you don't know, because winding, we only check winding short circuit. But what happens is sometimes the core will get earth. That is a problem in the core. So you will have a spark in between the core, the laminations. So those things can be identified with the FRA. That's the beauty of one of the beauty of the FRA. And the open circuit, of course, you will have a change in the mid and high frequencies. There will be looseness. That means there will be some bolt, that is a tightness will be maintained. That will be maintained by the spacers. If there is any problem in the spacers, that can also be identified. It will be visible after the that is high frequency 5 megahertz. And there will be bushing fault. Of course, we will have high frequency. It will be seen. And we'll come to the end. That is in the sense the offline method, that is turns ratio test. It's a simple test. It's like testing the turns ratios. I'm running short of time. So you have to see the change in the ratios. So you will have a measured ratio, and the nameplate is the standard ratio, which would have been there when the transformer is manufactured. So the change in the ratio gives you an idea of what is the problem, whether it is an insulation failure, core structure failure, or interwinding insulation failure. Now we'll come to the online method. Online method is the very famous method is dissolved gas analysis. Of course, I have justified with my finding that online measurement of SFRA is also possible. But here I am restricting myself to this one. So dissolved gas analysis, there's a gas chromatography. So chromatography simply means you have to first extract the gas. I already told you all the gases will be there in the oil if there is a depolymerization. The gas has to be extracted from the oil. You put a membrane, depending upon the pressure level variation, you will have the gas extraction. That can be identified, detected with thermal conductivity detector or flame ionization detector. So both works in a different concept actually. So there will be slight changes. And of course, after that, you have to put it in the oxide fuel cell, solid oxide fuel cell, through which you will have the peaks varying depending upon the gas concentration. And from that, you can identify what is the ppm level of the gas in the oil. So this is very, very tedious method. Previously, people used to do, they take the oil to the, like our blood test. If you give the blood test, there will be a collection center, and a person will be coming and collecting in the evening, and the next day they will go, they will test, and one day after they will give the result. Similarly, oil also will be taken from the transformer site, and it will be taken to the actual laboratory, and they will test. But nowadays, this can be implemented within the transformer itself, but it is costly. That's it. So these are all the gases which can be seen in the oil. And there is another method of understanding the concentration level of gas, that is photoacoustic spectroscopy, also called as PAS. And you have to give a laser, because laser gives an excitation to the gas molecules. So different gas molecules respond differently to the laser, and that is actually result in the macro level as a heat, which will cause a pressure wave, and you can use a microphone to detect it. All these things obey Beer-Ambert's law. The Beer-Ambert's law, you know that there will be a molecular observability, that is I have indicated instead of epsilon I have put E. Then the length of the light path, then C is the concentration. Based on that, you can understand how much is the concentration of all the gases. I have already told you different gases which are present due to the depolymerization. And the main gas, of course, in any of the cellulose compound, you will have three main components. One is carbon, and another one is hydrogen, another one is oxygen. Usually the carbon and oxygen combine, they are good friends, though they combine and they form carbon dioxide, carbon monoxide, and they escape. But the hydrogen is very detrimental, in the sense they exist as a single molecule, they form acid in the oil, and if they exist as a OH, they will form what you call as oxides. So that's very detrimental. And so we have a special palladium compound. Now it is available. This is the very, very recent trend. Actually, maybe it may be some 5 years or 6 years old. So they have a palladium hydrogen combination. So the free hydrogen molecules are absorbed by the palladium. But what's the problem is if you put palladium alone, there is a problem. So they always go with the alloy. So alloy comes with another problem. You have to make it an alloy with either silver or gold. You can understand the cost. Okay. And another way of interpretation is dissolved gas analysis is key ratio methods. And the key ratio means you should understand the key gases. So the ratio between the gases is the key ratio. And you have ethylene, carbon monoxide, hydrogen and acetylene. So all these things are very, very important things. And all these things are emitted because of a particular reason. There will be a winding short circuit, there will be a PD or a high energy arcing. So all these things have specific reason behind it. It's exactly like blood. Okay, so blood contains, imagine you have a lot of white blood corpuscles, that means there is some problem. It is going for fighting. If it is a thrombocytes, there is another problem. You have a wound, so it is trying to heal. So you have to understand. So exactly similar to that you have in the oil. So there are many methods. One of the methods is Rogers ratio method. He actually identified by the ratio of key gases. So these are the key gases ratios. So all these ratios will give an idea, and I have given the table. I will just upload this. You can read it casually and relax. Then Dornberg ratio method, that is also giving another idea of these key ratios. Instead of 3 ratios, he formed 4 ratios. And this is one of the famous method, the dual triangle method. It involves only 3 key gases. So CH4, you have a methane and acetylene, and you form a particular triangle. You find the meeting point. The meeting point gives you an idea. So what is the meeting point? I have given different meeting point T1, T2, T3, D2, D1 and DT. So I will just display the things. So what is PD is nothing but partial discharge. D1 here means discharge of low energy. D2 means discharge of high energy. So you can combine all these things, take the ratios, put a straight line from each of the thing parallel. You have to draw the parallel thing. So, if you draw a line from here, it has to be parallel with this triangle, and this has to be parallel with this line, and this has to be parallel with this line. So you will get a point. That point where it lies, it gives an idea of what is the type of the fault which is happening inside the transformer. This is one of the recent method in this. Instead of triangle, they have pentagon. The people are academic people. They always introduce new things. So we need paper, right? So these are all the ways of getting paper. And the final thing we are going to discuss is a partial discharge. Of course, the partial discharge is one of the electromagnetic radiation. So electromagnetic radiation can be seen by using the antennas. So ultra high frequency is the electromagnetic radiation, means you need to put an UHF antenna, and you can absorb it. And of course, the triangulation, there are many methods of identifying partial discharge, but the problem is partial discharge is like a guard. You can't say that only one point the partial discharge is happening. It is happening in the multiple point. So this is like predicting our blessed cyclone. So people are saying that one cyclone is there, and there is a model, and it is just moving, and it is coming towards Chennai. Then it takes a U-turn to Kadalur. So it's similar to that. Why it takes U-turn to the Kadalur? Because there is another circle which is rotating on the sides. So partial discharge is like that. So you have only one source of partial discharge, no problem. You can detect it perfectly. But God does not manufacture like that. You have multiple source of partial discharge. So you will have antenna. You will have a lot of garbage. Okay. Right. The next is the.
Excuse me, sir. Last 5 minutes, sir.
Yes, yes. I completed. I completed.
Okay, sir.
This is the last. I understand. Right. So these are all the PD waves. You can put an antenna and you can take it, and you can even take it using the physical quartz membrane and understand what is the type of electromagnetic radiation this time. There are many grating methods also. So you put a light, and depending upon the reflection, you minus the reflection, you get the transmitted light. You understand what is happening inside. That is the another way of doing it. This is interferometer. These are all new techniques for understanding the PD event. Apart from that, you have transient earth voltage detection, and this is understanding the electromagnetic radiation of PD through the tank. So you put a sensor on the tank, and when the PD hits the tank from other side, you try to triangulate. Putting the TEV sensors on the tank, you can understand. And similarly, you have the core, which is actually passing the earth wire. So from that also you can understand how much is the PD sensor. Nowadays, you have this method which is implemented. And thermal measurement, of course, the temperature is a very good thing, but the temperature you can't measure directly. So nowadays transformers are getting a lot of optical sensors implanted within the windings and spacers, but previously it was not there. So you can measure only the top oil temperature which is used. The last one is the vibration analysis. Of course, you can take this as a signature. Vibration is a physical phenomena. So when you increase the frequency of the signal, signal is nothing but your normal frequency. If it is 50 hertz, you increase double 100 hertz, then your core will vibrate. It will produce the vibrating frequency that it can be stored as a signature. So if you do the same 100 hertz for 40 years transformer, it will give a different vibration. So based on that, you can understand what is happening with the transformer. So these are all the references. I hope I have conveyed some meaningful information. If there is any questions, you can ask. Otherwise, we will. Jayalakshmi madam, is it okay?
Yes, sir. Okay, sir. Dear participants, do you have any questions? You can unmute yourself and ask, or you can post it in chat box.
Chat box. Okay, I have to come back. Okay.
We are having many types of monitoring methods, sir. Out of that, which one is practically possible in our country, sir?
Practically, it is possible. Everything is possible. Only cost. Practically, everything is possible. If it is not practically possible, diagnostic methods would not have evolved. It's only cost. So if you have a sophisticated instrument, you can use SFRA and all. If it is not possible, then it is not. Any other questions? Break down something, oil, explain. These are all the previous around 644. Okay.
You have asked many questions to us, sir. So no question for you, sir.
Okay, thank you.
Past 3 days, you have only interacted with all the resource persons. Today, many participants have interacted with you, sir. Really, it was a very informative and interactive session, sir.
Thank you.
Now, I request Mrs. S. Sangeeta, Assistant Professor, Department of EEE, Bharat Institute of Higher Education and Research, to deliver the vote of thanks.
Good evening, everyone. We extend our heartfelt gratitude to Dr. M.K. Ilampurnan, Sir, Professor EEE and Dean IQAC, Bharat Institute of Higher Education and Research, for delivering an insightful and engaging talk on condition monitoring and diagnosis of power transformers. Your expertise and in-depth knowledge on the subject have provided us with valuable insights into this critical area, enhancing our understanding and broadening our perspectives. Thank you, sir. Thank you once again for your valuable contribution to the success of this faculty development program. Thank you very much, sir.
Thank you. Thank you.
Thank you, ma'am. Dear participants, now we can leave and join session 8 immediately.